Hi, I'm 𝗦𝗵𝗿𝗲𝗚, and this is Balls Out Physics, Episode 2, The Gravitational Constant. Before I begin, I really want to thank everybody who commented on the first episode. The positive feedback was fantastic. I had no idea the video would be so well received. Thank you all for taking the time to watch it and really think about it. And even in some of the negative comments, there were some very good questions asked. And I would definitely like to revisit the plane problem after a few episodes. But there's some topics I'd like to cover first because I think it'll better explain the plane problem as we go along. And so the other thing I want to say is that I'm not claiming to be right about all this. When I first discovered flat Earth theory, I thought I could debunk it right away. But the problem was I couldn't. I realized that there were some very good points being brought up by the flat Earth community, and that's why I started this series, because I'm really asking for help here. I can't explain these things, and I've got a pretty strong physics background. I took 2 physics courses in high school and then a bunch in college to get my degree, and maybe I'm missing something, maybe I'm not. But one of my favorite sayings in the engineering world is, you learn 10 times more from your mistakes than you do from your success. This is what we always tell rookie engineers. This is what they told me. Don't worry about making mistakes. Don't worry about being wrong. Because when you are wrong or you do make a mistake, you want to find out why. And on the way to finding out why, you learn a ton. So never be afraid to be wrong, because you can learn from it. And no one on this earth who has ever lived on this earth has ever been right all the time. All the time. It's never going to happen, and it's never happened. So accept it. Learn from it. So anyway, this episode is mainly about gravity, but it's about the gravitational constant in the gravity equation. However, to get there, we need to start with some basic physics. And so I've set up a problem here with the Earth, represented by this blue ball, and me, or any other man or woman, standing on the Earth, and how we determine the weight of that person, okay? Or the force of gravity acting on that person. Weight and the force of gravity are actually the same, or at least that's the accepted belief in physics. Weight is actually caused by the force of gravity of the Earth pulling down on the object, in this case, the person. And so the bread and butter physics equation up here, one of the first equations you learn in Physics 1 is force is equal to mass times acceleration. This is what Newton based all of his 3 laws of motion on. And since his boy Copernicus, 150 years prior, had come up with the solar system, he knew that he needed to come up with an equation that would not only work on Earth, but would work throughout the universe. Okay? And so what this equation says is that the force acting on an object is equal to the mass of that object multiplied by the acceleration that the object is experiencing. Okay? And mass is defined as the amount of matter in an object. And in Physics 1, they hammer into your head that mass is the same throughout the universe. Only weight changes because the gravity on each planet can change. The gravity on the moon is less than it is on Earth. It's supposed to be about 1/6 of what it is on Earth. And so I was taking physics, and I had just taken chemistry, or I was taking it at the same time, I can't remember, but I immediately thought about the fact in the lab we were weighing things in terms of grams. And in the metric system, grams and kilograms are actually units of mass. But to determine mass, we actually weigh it, or weigh an object, and we say this is how massive it is. And so I thought to myself, well, if that's the case, if I took that same scale up to the moon, it would definitely give me a different reading because the force of gravity is less, and that's what's pulling the scale down, right? So how can that be? How can mass be the same throughout the universe? Does that mean we would have to calibrate our scales to work on the moon so that they show the same mass that we get on the Earth? Or do we use a conversion factor instead? Or how does that work? Does that mean that just all mass in the universe is actually defined on Earth? I don't know. I never really got that, but at the time I had been in school for a long time. I was 18 years old and I was ready to get out and go make some money, so I didn't really ask too many questions. However, I always questioned that and I always thought about it, and I've talked about this with some other people, and there are a lot of people that say, yeah, that doesn't really make a whole lot of sense. But it's accepted in the physics world. So anyway, that's mass. Okay, the mass of an object, the amount of matter in an object. The acceleration acceleration is defined as any change in velocity. Okay, so velocity can be measured in miles per hour, as I did show in the first problem, or kilometers per hour, kilometers per second, meters per second, whatever. That's the rate of velocity. However, acceleration is defined as any change in velocity. So in this example, if I'm standing right here on this Earth, okay, I have a velocity. I'm moving with the Earth. As you remember in the first problem, we said I'm in Central Florida. My velocity is probably around 900 miles per hour, maybe a little less, somewhere between 850 and 900 miles per hour. Okay, but since the Earth, I'm supposed to be standing on an Earth that is rotating. This direction of that velocity is constantly changing. Okay, so when I get over here, this is exaggerated, obviously, but now my velocity is pointing this way. So, even though I'm standing at rest, because of this theory, I'm constantly accelerating, because the direction of my velocity is constantly changing. And this will be better explained in the next episode when we talk about centrifugal force. So anyway, since weight and mass are different, weight is actually considered to be a force. This force of gravity, we have weight over here and weight here. Weight is equal to the force of gravity pulling me down. Okay? So this equation can be rewritten, F equals ma can be written as weight is equal to mass times little g here. And little g is considered the acceleration due to gravity, or the acceleration at which things fall towards Earth. Now I posted a link in the description to a trailer for the BBC series episode 4, Human Universe, in which Professor Brian Cox from the UK, travels to the Glenn Research Center in Cleveland, Ohio, to do an experiment with NASA's vacuum chamber. And in the experiment, they drop a clump of feathers and a bowling ball. And the first time they drop it when there's air in the chamber, the bowling ball obviously falls a lot faster than the clump of feathers. But when they remove all of the air from the vacuum chamber, both the feathers and the bowling ball fall at exactly the same rate. So what this little g says is that all objects accelerate towards Earth at the same rate unless there is some type of fluid preventing them from falling at that rate. And so the more dense something is, the faster it'll fall through the air. The less dense, the slower. It's just like in water. Something heavier or more dense, more massive will sink faster than something that's less massive or less dense. And if the density is actually less than water, it'll float. And the same with our air. That's how hot air balloons work. Or, blimps with helium inside them, or balloons. That's why they float, because their density is less than that of air. But when you get rid of air or any fluid, everything falls at the same rate. And that's a really great episode. I highly recommend you watch it. It's very interesting to see. Okay, so that's weight. Okay? And weight or force in the metric system is measured in newtons. Okay? So 1 newton, obviously they gave credit to the guy that came up with this, 1 newton is equal to 1 kilogram times acceleration due to gravity, or rate at which things accelerate towards Earth, which is 9.81 meters a second squared. So 1 squared. So 1 newton is equal to 9.81 kilograms times meters per second squared. Okay, remember that. A newton is really equal to units of kilograms times meters per second squared. 1 is equal to 9.81. Okay. So I weigh about 160 pounds. And in the English system, I could just say that's pounds mass. Or actually, I can say that's pounds force. But in the English system, we don't actually differentiate between with 2 different units between mass and weight. There is a unit called a slug that's used for mass, but nobody uses it. Or there is mass, but nobody uses. So if I say my weight is 160 pounds force, I can convert that to mass in the metric system, which is about 72.6 kilograms. So my weight in the metric system would be 72.6 kilograms times 9.81 meters per second squared equals roughly 712 newtons. Okay? That's my weight in metric units. So, over here, we have the equation due to gravity. Okay. And that says that the force of gravity is equal to the gravitational constant times the mass of one object, in this case me, this is represented by a little m, times the mass of another object, which would be the Earth, divided by the distance between them squared, which in this case would be the radius of the Earth. Now you should actually add the distance to my center of mass from the Earth's surface, but it's so insignificant that it doesn't really matter. Okay? And the gravitational constant, which I should have written down here, is equal to 6.67408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? So if you plug the mass of Earth, which I have written here, which is 5.9726 times 10 to the 24th kilograms, really big number, my mass, 72.6 kilograms, and the gravitational constant, and the radius of Earth, which is 6,371,000 meters, you will get 712 newtons, roughly. Pretty close. Close enough to say it's the same. To say that to accept the fact that, well, the assumed fact that gravity is causing this weight. And that's why I have weight is equal to the force of gravity on here. Okay? This is what is taught in physics. That this force of gravity actually creates my weight, but there's just two different ways we can calculate it. Okay? But Newton came up with this before he came up with the equation for gravity. And in fact, Newton only proposed the equation. He didn't actually finish it. He said, from looking at the solar system model and watching things in the sky that he thought, or he assumed were orbiting Earth based on Copernicus' work, that the force of gravity was proportional to the mass of one object times the mass of another object divided by the distance between them squared. Okay? He said they're proportional, they're not equal. So what this means is, if either one of these masses go up, or both of them go up, the force of gravity also goes up. But as the distance between them increases, the force of gravity goes down. And as you can see, this is square, so distance plays a big part here. So, he eventually proposed that he needed this big G up here, this gravitational constant. And he didn't know how to determine that, but he did know that the units would be what we have right here, meters cubed over kilograms times second. Now, he might not have been using the metric system then. I haven't actually looked into that, but he would have been using something similar. So I'm just going to assume that he used metric units, because if you combine the units in this proportion right here, you would get, assuming the masses are measured in kilograms, you would get kilograms squared over meters squared. And if you multiply that times this factor down here, you will end up with kilograms times meters a second squared, which is equal to a Newton, or a unit of force. Okay, just like I showed in the original equation, the original bread and butter equation over here. So, that said, he theorized that there was this gravitational constant, but he didn't actually figure it out before he died. And it wasn't until a little over 100 years later, 120, 130 years later, that a man named Henry Cavendish came along. Henry Cavendish was very wealthy, and he did a lot of things apparently. I've listened to some very respected physics teachers praise his work, and I've studied some of his work, but mostly what I was interested in was how he determined this gravitational constant. Okay? Cavendish apparently had a lot of property, a lot of money, and he set up an experiment where, get rid of all this. Now let's go back to where we just have these two equations. They haven't figured out the big G yet. They do know the radius of Earth, though, because they knew the circumference. So they knew the radius of Earth, but they didn't know big G, and they didn't know the mass of Earth. Okay? So going back to Cavendish in 1798, Cavendish built this box, this wooden box on his property. Looks something like this. Okay? And in this box, there was a pulley with a rope leading outside the box, something like that, a little handle on it. And what hung from it was this thing called a torsion rod. It's something like this. And on the ends of the rod were these large lead balls. And on the inside were these smaller lead balls. Something like this. Pulley right here. And he used lead because it's very massive, it's very dense. And he, apparently, according to the history, he knew that he had to get away from the box because his gravity, his mass, would affect the experiment. Assuming that this is correct, that the force of gravity is, there's a force of gravity between any two masses, not just the Earth and us. All masses have a force of gravity on each other, or create a force of gravity on all other masses based on this equation and the proportion that Newton came up with. So he somehow set up some telescopes that went back to his house. Keep his house off the board, just assume his house is down here somewhere. So he could observe this experiment, and somehow he calculated big G from this. Okay? Well, when I started researching this, I said, okay, well, let's see some examples of a modern day torsion rod experiment that somebody's built that shows how this works. Well, I couldn't really find one. I actually had a lot of trouble finding one. Actually, one of the physics professors that was praising him had a little model that he held up and was joking that his TA couldn't get it to work and got frustrated with it and gave up. And I'm thinking to myself, over 200 years later, we don't have models of this, or repeats of this experiment all over the place to determine big G? It didn't make much sense to me. So I said, okay, well, going back through the history, let's assume that he did this somehow. He's a really smart guy, and we just haven't been able to get it to work again. Okay? So, Cavendish determined big G through that torsion rod experiment. Okay? So he calculated it to be the value that we're still using, which is 6.67 408 times 10 to the negative 11 meters cubed over kilograms times seconds squared. Okay? He determined that from that experiment. Let's assume that's correct. So now he must have been really excited because he knows what this big G is. He knows what his mass is, or any other mass of an object on Earth. He knows what the radius of Earth is. So he can set these two equations equal to each other. He knows that weight and the force of gravity are equal. So what he did was, you can look this up, this is exactly how this was done. Weight, which is equal to mass times G, or the mass of the man, or whatever object he's using, in my case I'm going to say me, is equal to big G times the mass of the man times the mass of Earth divided by the radius of Earth squared. Now immediately, you can cancel the mass of the object, or me, out, because they're in the numerator on both sides. This is really mg over 1. Okay? And now, let's come up here. You can solve for the mass of Earth. You can multiply the radius squared times both sides, and that comes over here. Cancels on this side, and then you can divide by big G. So you get ME, and this is basic algebra here, is equal to little g, the acceleration due to gravity, or the rate at which things accelerate towards Earth, times the radius of Earth squared divided by big G. And that is how the mass of Earth is calculated. That is the mass that NASA has on their fact sheet, where I got all this information about the Earth's radius and the mass of Earth and everything for this problem. Okay? So I looked at this and I said, okay, that makes sense, but I still had the question in my mind saying, wait a second though, why can't we do this torsion rod experiment now? There's some, I looked into this more, and right now there's debate going on about what this big G actually is. Some people are arguing and saying it's different. And they're doing experiments on an atomic and a subatomic level where they're looking at particles with very powerful microscopes and observing how they're attracted to each other, which they say is because of gravity. Now, I can't go buy an electron microscope and do those experiments myself to check it because I don't have that much money. And I don't want to try to build a torsion rod experiment because from everything I read, it sounds like it's not going to work. So I'm also going to spend a lot of money on that. So I'm really questioning, this big G. How did they come up with that? But then I started to look at this algebraic expression that was written. Get rid of big G again. Say, well, what if they were so sure about this equation due to gravity, or this equation of gravity, that they were having trouble coming up with G, that they did something else to determine it. What if they did this, or Cavendish did this? What if he said G is equal to the acceleration due to gravity, as he would have called it, times the radius of Earth squared times the mass, or divided by the mass of Earth. Of course, he doesn't have the mass of Earth, right? Well, he does have the radius of Earth. And at that time, they definitely knew how to calculate the volume of a sphere. The volume of a sphere is equal to 4/3 times pi times the radius squared, or cubed actually. In this case, it's the radius of Earth. And so since they know the total volume of the Earth, they know that if they could figure out the average density of Earth, they could multiply that by this volume and get mass. At the time they would have known the density of water and the density of sand, the density of ground rock, the density of iron, the density of gold, the density of silver, the density of all these things were already determined. And to determine the density of something, it's really just the mass per unit volume. For example, we'll call them rho. Call rho density. Rho water is equal to 1,000 kilograms per meter cubed. What that says is in 1 cubic meter, if you have you have something that holds a cubic meter of water, it weighs 1,000 kilograms. If you have something that holds 2 cubic meters of water, you say the density of water 1,000 kilograms times 2 cubic meters. You see the cubic meters would cancel. You get 2,000 kilograms is how much it would weigh. Okay, so you definitely know the density of water back then. You definitely know the density of, let's say sand and soils, which is roughly 1,200 to 1,600 kilograms per meter cubed. And they definitely knew the density of iron, because they were building things out of iron a long time before that. We'll call that rho I. And that is equal to 7,780 kilograms per meter cubed. Now, whether they were using metric units again, I don't know, but they would have had their units that could be converted to the units I'm using now, or the metric units I'm using now. Now, based on the volume of Earth, let's call that VE, the volume of Earth is actually 1.083 times 10 to the 21 meters cubed, okay? If you use NASA's fact sheet with their mass of Earth, which is 5.9726 times 10 to the 24th kilograms, and you divide that by the volume of Earth, you will get an average density of Earth, I'm going to call that rho E over here, of 5,515 kilograms per meter cubed. Okay? So, looking at this, just looking at water and soil, water is, well, the average density of Earth is over 5 times greater than the density of water. And water is actually pretty dense. If you've ever done a belly flop into a pool, you've seen you've experienced how dense it is. But, the average density of Earth is 5 times that of water. It's also a lot greater than soil and sand, which is really ground rock. But then you look at the density of iron and notice that actually the density of Earth is pretty close to the density of iron, based on everything that was calculated, the mass that came from this relationship up here. So I started thinking, this is pretty high, and that's exactly why we theorize that the Earth has an iron core, because this is the average density of all the stuff in Earth, all of the elements, everything on the periodic table that we know. Now, at the time, they didn't know all the elements on the periodic table, but they knew a lot of things. So, what I'm saying here is, if you follow where I'm going with this, how do we know they didn't guess, or that Cavendish didn't guess this mass of Earth, and then just use it to solve for G, and then do the opposite and say that he did this, that he solved for the mass of Earth using that value of G? It's the same thing, just based on the algebra. And then if you plug both of those values into this equation up here and use the mass of any object, whether it's a man, a horse, a carriage, anything, and use the radius of Earth, you're going to get a force that's equal to the weight you get for that same object if you just multiply the mass of that object's time the acceleration due to gravity, or the rate at which the acceleration at which things fall towards Earth. Seem far-fetched? I don't know. The fact that we can't really get this experiment to work, this torsion rod experiment to work, is perplexing. Very perplexing. We have to trust that they didn't do this. But what if they did? Our entire solar system model stems from this. Assuming that this is correct. Assuming that this big G, this gravitational constant, is correct. So, I don't know. I don't know what to think. But, one thing I do know, based on my research, another thing I found out based on my research, is that Cavendish and Newton were both Freemasons. It's a very big club. And back then, the average person couldn't even write their own name. So people slowly were introduced to the sciences. More and more people were introduced to the sciences over the years, and it wasn't just the wealthy people over the years. And I know there's a symbol out there that a lot of people have been trying to figure out. It looks something like this. You ever seen one of these before? Found them on a Freemason lodge. It's kind of ominous symbol. First time I saw it, I was like, what was that? What is that? It's very strange. Compass and a protractor. The big G in the center of it. What does that stand for? I don't know. Could just be a coincidence. Some people think it means geometry. Some people think it means God. I don't know. Some people even think it means Gnosticism. I've done a little research on this. Who knows? But maybe that's just a coincidence. I'm just asking questions. But in the next episode, we'll look at the relationship between this equation and the centripetal force equation and how it was used to develop our solar system. Till next time, peace.